Hello everyone, my name is Alessandro. My supervisors were Stephane Caro and Takemura Kenjiro. And my project focuses on trying to design and then build, hopefully next year, in the laboratory, a prototype for a gecko robot. So a bio-inspired robot based on the gecko, so something that can move and crawl and most importantly climb and attaching to surfaces. The state of the art currently, I found this robot that was proposed in 2019, and this robot uses soft actuators which are pneumatic, and the mechanism it uses to stick to surfaces are suction cups. So again, something pneumatic. And being a soft robot is important because it can protect the robot itself when falling. But the main problem I see and that I want to try to solve or work towards a solution is that the pressure source cannot be carried by the robot. As you can see, there are tubes to bring the air pressure to the robot itself. So the robot must be tethered to something. As you can see here, the pressure supply and the control board also are always attached to the robot. Another robot I found as the state of the art is this other robot proposed in 2015, and this one is mechanical, so my idea would be to try to use soft actuators. And I chose this one because it uses electroadhesion as the way to stick to surfaces, which I think is a very good solution to the problem that the first robot had, which was carrying the pressure source. And this type of robot would be able to stick to surfaces using electrostatic forces. So except for the high voltage, it doesn't need to carry any other pressure supplies. And the way I want to merge the two solutions is using a type of actuator that is developed in the Takemura Kenjiro laboratory in Keio University, which is called Electro Conjugate Fluid actuators, which I will talk more in depth later. So the main improvements are obviously trying to reach a smaller size and smaller weight, then work towards reaching an untethered mobile soft robot. This needs to be feasible, obviously, so even if I will not reach exactly a perfect robot that can do everything and that is also untethered, I still want to work towards solutions that go into that direction. And other improvements are, for example, floor and wall ceiling transitions, which means having a robot that can bend its torso in this direction, so being able to stick to a wall or from a floor then to a wall or from a wall then to a ceiling. For example, the previous robots I showed here do not have any actuator that can bend in that direction to complete this type of transition. The last improvement I would like to try, if I have time, is to implement an active tail. So again, a tail that can move, that can bend, because I have read many papers that describe how having an active tail improves a lot climbing performances. The tail can act as a bicycle kick manner, so it can push against the wall in order to reorient the angle that the robot has in comparison to the wall. And it can also shift the center of mass of the robot and also help in turning while climbing on a wall. The actuators I want to try to use, as I said before, are Electro Conjugate Fluid driven actuators. Electro Conjugate Fluid is a type of fluid that reacts to strong electric fields by creating a flow when subjected to high electric field. And this type of flow that is created by some needle and ring pair electrodes are used with this mechanism, which is, these are the actuators developed in the Takemura lab. They used it to build the hand I just showed you, and I want to use them as the legs of the Gecko robot. The idea behind this type of actuators is that the pressure source and the fluid itself are already inside the actuator itself. So you can see it has two chambers, and these four are the needle pair electrodes, needle and ring pair electrodes that create the flow of the fluid itself inside. So these two push the fluid from this chamber to this one, and the same do the other two, pushing it towards the center of this chamber. So in this way, this chamber gets filled, and this one is unfilled, and this creates the bending of the actuator. This type of actuators, though, are only bending in one direction, and they work at around between 4 and 6 kilovolts, so a lot of voltage, but the main idea is sharing that voltage between the Electroadhesion and the actuators, so using the same high voltage. The good thing is that even though they require a high voltage, they require very, very low current, like 30 microamperes, so the actual power consumption is very low. This also means less strong force output, but it will not be needed as high. As for the electroadhesive pads, I had to change idea many times, because at first I wanted to work with this type of pads that were developed in another lab in KU University, but I discovered that the company that produced the gel stopped providing the materials, so the research stopped, and the professor couldn't help me in my research. So I found a different solution, which was an Italian company named Adaptronics, who developed literally the perfect product for me, and I tried to apply for an internship. I had a meeting with them, but then they said we don't need any interns right now. And lastly, I have some contacts that my supervisor gave me with a laboratory in Tokyo in a research institute, and maybe I will find out more about their product. The other aspect is that I need to develop a bending actuator that can bend omnidirectionally. As I said before, I would like the torso to bend also in this direction, and I need this direction to crawl upwards or to move forward. The laboratory already developed, this is a bidirectional bender, so it can bend in two directions. I would like to find a way to build an omnidirectional bending. For example, this has 2 chambers, and this one instead has 3 chambers in order to bend omnidirectionally. The problem of this paper was that the actual movement, the actual bending of the actuator was so small that it's basically useless. So I will have to find a way to improve on this, and it will be part of my future work. So the work I did so far was setting up a design optimization problem with the two goals in mind. The first goal was, let's decide on a specific design that I want to follow. At least a first design. And then the second purpose of my design optimization is to set up something that can later be refined with more correct equations and force and bending formulas. Because right now I used to build my design optimization problem, I used formulas that I could find, data that I could find on papers, but the work after this is develop the simulation for each single individual component, starting from the leg actuator, then later the omnidirectional bending actuator for the torso, and then later also for the electroadhesive pads, in order to have specific and very precise formulas to put them into the same design optimization problem and find the perfect values for the design variables, which right now are, for example, the length of the actuator of a leg, the thickness, i.e. the diameter, for the torso also, then the maximum voltage that I want to apply to both the pads, the electroadhesive pads and the actuators, and lastly the tail. So what I did was set up an optimization problem that tried to minimize a triple objective function. The three objectives are try to minimize the mass of the robot, the size of the robot, and the voltage applied. Then the work included finding and setting up in the code the linear constraints and the non-linear constraints of the robot. Because what I care the most is that the robot must work in the way I want. So for the linear constraints, for example, the first one is voltage saturation. The actuators over 6 kilovolts start to saturate, so we need to have a lower voltage than that. Then other constraints are I want the length of the tail to be a certain amount for it to be useful. And then for the linear constraints, the main important ones are the first one, so the electroadhesion forces must hold the robot, both in the shear direction and in the normal direction. If I imagine my robot one day climbing on the wall, it needs to not fall off. And if it is able to crawl on the ceiling, it also needs to not fall off in the normal direction. Then other constraints were, for example, the torque that the actuators provide, because they need to be able to lift the leg of the robot, to lift the pad. And for example, the torso needs to be able to lift the whole upper body. Then I also set up a minimum relative gait displacement, so basically how fast the robot can walk for each cycle of gait. And then some minimum dimension ratios. These are needed because the aspect ratios of the actuators matter a lot in how much they bend. If an actuator is very small and thick, it will bend way less. So these are some of the formulas I used for the constraints. Again, I found them in the papers, and they will be refined once I will complete the work on COMSOL to simulate each individual component. And lastly, I set up also another optimization problem separated, which was to find what is the minimum relative gait displacement that I can put while keeping the problem feasible. And so here we try to maximize this minimum value that I want to put in the constraint. And here are the results. The constraints were feasible, so the main point is to find out that the design is feasible and it can be built properly. Here are the results of the constraints and to check which constraint is active and when and how it impacts the design problem. And yeah, so the future work, as I already told, is working on the console simulation, which I already started, but it's quite difficult. So I don't have good results yet. And starting from the simplest actuator to the more complicated, then the Electroadhesion pads, and put the results that I get from console into this optimization problem. And that's all. Here's the bibliography.
Thank you for your presentation. You have presented some work about optimization. It was not completely clear for me if it is a work that is done in a paper or it is your work.
No, the whole optimization is my work because the design of the prototype is new. Nobody yet proposed a robot that works with ECF actuators and with Electroadhesion. So yeah, the work is mine, and
because you said when you give the constraint, you said this constraint came from the paper.
I meant the formulas used in the constraint. For example, how the electroadhesive forces are modeled, those type of formulas. For example, these type of formulas, these are from the paper that was published by the professor that worked on these electroadhesive pads, which at first I was supposed to use. Then we discovered no. So that's also why I say the formulas needs to be refined, because they are not precise, they are not necessarily what I'm going to use, especially for the electroadhesive pads. Although they may be similar, I want to refine them using formulas that I get from the simulation.
Okay, if you go to your form after, you have a constraint, when you have a list of mathematics after,
Here?
this one, what is the meaning of C6 equal minus L leg minus
This is
C
the...
What is this?
It is constraints that work on the aspect ratio of the actuators. Because if, as you can see, there is length and diameter, thickness of each actuator, the leg, the torso, and the tail. And the actuator's bending angle is depends a lot on the aspect ratio between its length and its thickness. So there must be a minimum ratio in order to have the bending angle required. That bending angle can be more, so the constraint is inequality.
Thank you. Now, another question. You say that your actuator has a very high voltage. Is
Yep.
it a problem? Is it a practical problem of safety?
Yes, obviously, because high voltage requires good insulation in the materials, first of all, and obviously you need to produce that high voltage. But the idea is that since you need very low current, you can use step-up voltage multipliers in order to still have a very compact circuit that could be mounted on the robot one day, so that all the power needed, electric power and pressure source is on the robot itself, so that it can be one day untethered.
So the objective is an autonomous robot.
Yes, because I found that having a robot that can climb is very, very useful to any type of work. But if that robot needs to be always tethered to something, then the applications are really, really diminished.
Can you give her some applications of such a robot?
Okay, for example, maintenance in difficult environments, or exploring also.
With a camera?
But yes, exactly. One very cool application I thought about is working in space. For example, if you imagine having to maintain a satellite in space on the outside, a robot that can move and stick to surfaces is very important, not to lose it, obviously. And this type of principle, the electroadhesion and the actuators, in theory, could work in space. The problem is the materials and the care you need in order to build something like this that actually works in space is very, very difficult, and obviously not in the reach for me at this moment. But yeah, that could be an interesting application.
Yes, it was not really clear for me how it sticks really on surfaces.
Yeah, the principle is electroadhesion. So on the electroadhesive path, there are electrodes that are printed on the pad itself. Usually they are printed in a interdigitated fingers setup, and these create electrical fields that are around each finger. So it polarizes the surface where it sticks to. So it creates electrostatic adhesive forces by polarizing the surface itself.
Okay, thank you.
Does it work with all surfaces, or you need specific material?
So all surfaces is difficult to answer because it depends on how rough the surface is. It also depends on what type of the permittivity of the materials. As you can see in the formulas here. As you can see in the formulas here, the permittivities of the two materials are what make the D in the formula itself. And they also appear here and here. So different materials will have different situations.
Thank you. So I have, well, I don't have so many questions, just a few remarks. So you in your slides, you mix things that come from you and that do not come from you. So it would be really much better each time you put a figure, an equation, whatever, to put the reference on the same slide, so everybody knows if it's something that you did or that someone else did.
Yes.
And I guess that, so here I don't quite get how you came up with the coefficients like 3, 5, 5.
They come from the paper on the actuators. They describe how the aspect ratio impacts the bending angle.
Mm-hmm.
And the bending angle required, the minimum bending angle required for each actuator, is more or less empirical for now. Again, that's why I say this is a design optimization problem that is a base and will need to be refined.
Okay.
And yeah, for example, the leg actuator has a lower coefficient because it doesn't need to bend more than 90 degrees for the robot to complete a cycle. While the torso could need to bend more, and also it also comes from the fact that it is an omnidirectional bender, the torso and the tail. So so as you can see here, making an omnidirectional bender that bends a lot might not be that easy. So having a higher coefficient could simplify that.
Okay. And on the overall figure of the robot, so you said that you want to make it autonomous so that it doesn't have to be tethered to anything. Maybe you can also control it by radio or whatever, so it doesn't
Yes.
have to be autonomous, and yet you don't have any cable.
Yes, I think this is a project that is maybe too much ambitious, because
Yes,
you
for sure.
could work on this type of robot way too much. So discussing with my supervisors, we decided that first of all, it is best to first develop this type of actuator, then develop the electroadhesive pads, and start testing just with a like an inchworm type of robot that moves like this, just with the torso and two electroadhesive pads. And if I can achieve that, I would already be very happy by the end of the next year. But yeah, the idea behind this comes from a more ambitious project that would require much more work, and I don't know what I will be able to do.
Yeah, because if you want to make it autonomous, well, first I guess that it will not be a microcontroller, it will be something a bit more powerful. Maybe you will need to add some kind of exteroceptive sensors, so it will add some weight. So
a very, very cool
has to
thing
be-
is that the electroadhesive pads that the Italian company developed, which I said it looked like the perfect product for me. I said so because they also had already some AI software. I don't know how it will work because it's private knowledge, but they had already AI software that could recognize the type of material and also the surface, the amount of adhesive surface, how much of the area of the pad adhered. And that could tell a lot of things, because imagine you just have a tape on the floor. The robot can already follow the tape just by knowing it's sticking to that type of material instead of something else.
Okay, thank you.